Okay guys, this is the fourth lesson of 4. It's a really short module. Before you get here, make sure you've done lesson 1 density, lesson 2 states of matter and changes, and the big one, lesson 3 on specific heat capacity and latent heat. And the fourth and final one is a triple science only topic, which is all about particle motions in gases and the pressures that they create. So the page number for this is page 41. It's pretty straightforward. There's no real tricks to it. So here we go. Well, that should have been a scroll. So we've talked about gases before and about how they're low density, they have lots of vibrations, they fill the container, and they're highly compressible. We're going to go a bit further with that now. We'll be linking into the idea that vibrations are kinetic energy, which was lesson 3. Let's make a start. So today's title is gas pressure. So when scientists are thinking about gas pressure, they have what's called an ideal gas. And there's a set of assumptions that come with this. If I drew a box and I put myself some particles in there, it never works when I want it to. There we go. And I put some particles in there. In an ideal gas, scientists assume that these are point-like structures with no intermolecular forces between them, and that they're moving at very, very high speeds. So if I come off there and I make my arrow nice and thin, we assume they're moving with great velocity and they're bouncing off the side. I'll just hand draw them. There we go. So no intermolecular forces and they're bouncing off the side at very high velocity. So we assume that they are point-like, that they have no internal structure, and that they have no intermolecular forces. So it's the only way you can deal with particles, like the theory of them at this point, keeping it nice and simple. So here we have it, an ideal gas. So get that copied in. And what have we got? We've got high kinetic energy and collisions with the walls. And they also collide with each other, but for this lesson we're interested in collisions with the walls. So let's zoom in on one of these collisions and we'll go over to red. When a particle hits, just like if you were throwing a ball against the wall, it's going to impart a force. And here we're going to have a force. And we are now talking hundreds of trillions per second, even on something small like a balloon. It is absolutely mind-boggling how many particles are in a balloon and how many collisions per second there are occurring. So many that when you look at a balloon, it appears stationary, but if you think about it, every one of those particles is hitting the side of the balloon and forcing the balloon out, while outside, I'll do those in blue, there are particles in the air hitting it, pushing it inwards. And it's the outward pressure, the particles in there, there's a higher density of particles because you blew the air in, and they're hitting the outside, the inside like that, forcing it out, compared to the air that is outside bouncing off it, trying to push it in. It's a remarkable amount. Crazy. I don't know the exact number. So we have particles hitting the walls and they're creating a force. And if you remember in year 9, if we were to turn this into a bit of a 3-dimensional object, so if I just add another dimension there, third dimension. If we were to take a square area of this, so 1 centimetre squared, what we've got here is we've got force over area. And when we have force over an area, we have a pressure. So the pressure of a gas is caused by the force of the collision spread out over an area of the container. So we'll put that in writing. So the particles collide with the surface of the container. Creating a force. This force acts over an area creating a pressure. I'm going to highlight my keywords in a minute. Okay, so we're starting to dip back in on the stuff we've learnt before. It really helps. So we've got a force acting over an area, creating a pressure. And if you think, that's almost word for word that introduction lesson I taught you in year 9, when we started off with a bed of nails sandwich. A force acting over an area, creating a pressure. Okay, so that's where pressure comes from. It's the kinetic energy of the particles, and the particles hit the surface of the container, and that creates the pressure. So let's have a look at how we could change that now. The first thing is, let's change the volume. We're going to take 2 balloons, and in each balloon we're going to have exactly the same number of particles. One balloon we're going to make quite small, and the other balloon we're going to make quite large. There we go. But into each we're going to place the same number of particles. So we'll choose that, and we'll try and fit 10. 2, 3, 4, 5, 6, 7, 8, 9, 10. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. And straight away you can see that the pressure is going to be different. Have a little look. Here, the number of collisions per second are going to be higher, more collisions per second. So that's going to increase the pressure because there is, so if we put more force equals more pressure. More collisions per second, isn't there? So more pressure. But if we took that balloon now and somehow we could stretch it out with the same amount of gas, here we're going to have less collisions per second. Particles have literally got to go further before they hit the surface. So that's going to reduce the pressure. So this time we're going to have less collisions, which is going to cause less force, and no prizes for guessing, less pressure. Like that. So that's the effects of volume. As you increase the volume, you decrease the pressure. So it's an inverse relationship. There's also another thing you can do, and you may have noticed this when you pumped up your bike. Some of you are probably having quite a lot of bike rides at the moment. I know I am. And that is doing work. So doing work on a gas. I'll explain what I mean. We've already talked about this concept of doing work, and that is where you move something, and in our case we put it on a table, didn't we? We put a bag up on a table. So the concept of work is doing something mechanical, and that is then a transfer of energy, and in this case it was mechanical work. But what about in the case of pumping up a bike? Well, if we think about it, let me see if I can draw this nicely. Come on, I want just a nice rectangle. I'm going to draw a cylinder, like the inside of a pump. I'm going to draw the handle, and there we go. And then I'm going to draw the actual cylinder that the gas is in. I'm going to draw that in dark green. So we'll go along like so. There's a reason for me drawing it out. It'll be all clear in a moment. And we go along there. Excellent. Not quite right. Okay, we'll put our gas in there. So you pull the pump out and in go the gas particles. There we go. So the chamber's open. Right, here's how it works. In fact, I'm going to take some of those off because there's a reason. I'll be doing something with them in a minute. We're going to grab the handle. So we're going to grab the handle around here. And we're going to push the handle down. We're going to move it down like we're pumping the gas. We're going to have to do work to overcome the energy that these particles have. They have potential energy, if you remember. And as we grab them, we're physically moving them closer together. So we're moving our gas particles into a higher density. We're squeezing them like so. And as they get closer together, the temperature is going to increase because their kinetic energy is going to increase. So the work that we do, moving the handle down and decreasing the volume, increases the kinetic energy. And if we look back at lesson 3, we saw there that the kinetic energy store is the amount of vibrational energy they have, and that's the temperature. Okay, so the more energy they have, the more internal energy, if that makes sense. Have a look back at your notes. So if I hop back here, what we can say is, as you do work on a gas, the work energy, the work energy is converted into the kinetic energy store. And because the kinetic energy store is the temperature, so we'll put that, we'll make it really clear. Since the KE is, now we put the directly proportional to temperature. Since kinetic energy is directly proportional to temperature, the gas gets hotter. And what other thing increases? So we've reduced the pressure, we've reduced volume, ignore that. We've reduced the volume by pushing the pump inwards, so volume's gone down. But what about the pressure? What do we think? Well, if the temperature's increased, then that means they have more vibrational energy, more kinetic energy, which means the number of collisions and the force that they hit the walls with is going to increase. You know, if you throw a tennis ball harder, you're going to generate a larger force on the wall. So the pressure increases because both the frequency of collisions, so there's more of them, and the let me get it right, and the force of collisions increases. Okay, get that colour coded in, put it in a blue. Okay, so that goes up, temperature increases. Anything to do with temperature always gets highlighted red. I always think of it as getting hotter. And volume in yellow, because why not? Right. Now, at the turn of the Industrial Revolution, this was hot science, so to speak. And it was hot, and it was the key driver of the Industrial Revolution, because what you're talking here is steam engines. And steam engines mechanised our transportation and our workforce. We created machines which led to where we are today with so many made things. So knowing how volume, temperature and pressure all interplayed was key to this. So lots of scientists made their name creating equations for that. Now, the one that we're going to do is a deceptively simple one. And what it says is, and we'll call it the gas equation, all we have to do in this one, we used to, in the previous curriculum, look at all three, temperature, volume and gas, pressure. In this, we don't. All we have to look at is pressure times volume is equal to a constant. Now, you're asking yourself, what's the constant? Well, the constant is anything that you get given in the first part of the question. So if I take this, if I'll go to a second page, e.g. question 1, and the question might look like this. Find the constant if you have a balloon and the pressure is 2 pascals. And if you remember, 1 pascal is 1 Newton per metre squared. Okay, so we'll be using pascals. And the volume is equal to 0.1 metre cubed. I think I'm still way off. So in this case, P times V equals 0.1 times 2 is 0.2. And it's a unitless constant. Now, why do you need to do this? Well, now if the second part of the question is you squeezed the balloon smaller, I think I've spelled squeezed wrong. I don't know. It's late. It's 25 to 11. Now, if we squeeze the balloon, no gas has escaped, but we've made it smaller. And the volume has now gone down to 0.01. And the question now is, what's the pressure? And so we can use this idea that it's a constant. We know that 0.2, the constant we worked out, has got to be equal to the pressure times the volume. And we know the volume is 0.01. So if we rearrange that, we can do 0.2 divided by 0.01 is equal to the pressure. And that will give us an answer in our case of 20 pascals. So it allows us to take a system at the beginning, find the constant, and then we can find the pressure or the volume of the other thing after it's been changed. That's why you find this constant. Now you may see it written out, and I much more prefer it written like this. P1 V1 is equal to P2 V2. So if I was going back to my question now and tidying it up, if I say this is red, P1 V1 is equal to I'll do it in blue, P2 V2, like that. And it's just so that you know which ones are your P's and your V's, because it's easy to get them mixed up. Scientists like their algebra, and unfortunately it can get a bit confusing with your letters. So you may see it written out like that, and I much prefer it like that. When you do this constant, people get hung up on, well, what's the number? It could be any number, depends on what these numbers were. But once you've got it locked in, tick, you can then work out any missing pressure as well. Final thing to say, and I missed it right at the very beginning, and it's been bugging me, is we need to include the word random. It is most definitely random motion. And it's this random motion that you may have come across in biology if you've done diffusion. in the textbooks it's funny. They talk about a smell, and everybody knows we're on about a fart. And they talk about the random motion. So if we introduce a smell, so like that. This could be spraying a deodorant can. It could be anything where one gas mixes with another. But here we have the smell, and it's at high concentration. Hopefully I think this is in year 10. Can't remember now. But it's this random motion that causes the particles to shoot off. They buffet against other particles, and it actually takes quite a while for them to thoroughly mix. But without that random motion, gases wouldn't mix, and chemistry wouldn't happen, and life wouldn't exist. Same with liquids, and then they move off like that. It's slower for liquids, quicker for gases, and eventually the particles then move around and distribute themselves based on the random motion. Now this motion, you don't need to know it, but it's called Brownian motion, and it was one of the first bits of evidence for atoms, because you could take let me get this right. Take a liquid that you can't see, and onto it you put just tiny little dots of ash or soot, absolutely microscopic, and you would see them jiggling. They would literally vibrate, and it was from the microscopic particles hitting them and bouncing off them, causing them to vibrate. So Brownian motion, worth looking up. It was a really key science experiment. Anyhow, papers will be at the bottom, questions to have a go at. I'm going to set a test for Wednesday, so if you can copy this one up, make sure you've got the other three, then do all the questions, do a practice on Tuesday, and then Wednesday from the morning sometime I'll post it as a Google form. And if you could get that done for Friday, and then Friday afternoon I'll do a live Zoom marking scheme again. And that's it. Take care. Bye bye.